Okay, hello everyone. Once again, I want to apologize a bit for this appointment that is taking me away. It's something I do not want to do, and I'll try to guarantee it never happens again. But I suppose some of you are rejoicing. You don't have to put up with me on a Friday. So anyway, we're going to talk about section 6 in our introductory unit in calculus here today. We're going to be doing some limit laws, some more advanced limit problems than what you had in section 5. So that's where we're kind of heading. And the limit laws that you get today will be fundamental in establishing the derivative and the various derivative rules that we will run into in unit 2. So that's where we're headed today, limit laws and so on. As you can see, I'm doing this from my home. So if the phone rings or if the cat starts meowing, you understand why. All right. So let's get started. So I'm going to switch to my other camera. And it looks like I'm getting some oscillating shadows going up across that. I hope that's not a problem for you. But we're going to start with the limit laws and see how this goes. Oh, what is this? We had a Marine Corps recruiter talk to our class today. He told us all about the rigors of boot camp. The 4 a.m. wake-up calls, the 20-mile runs in full combat gear, the obstacle courses with barbed wire and live ammo. Well, that doesn't sound too appealing. Then he held up for comparison a college calculus textbook. Smart man. Yes, he couldn't hand out the applications fast enough. All right, here are the basic limit laws as we will use them. Now, I am about to show you demonstrations of all of these laws. What I'm about to show you is a demonstration. It is not a proof. But for our course that we're doing a survey course in which we're kind of going through this with lightning speed, we just don't have the time to get into a proof of all of these. But I think the demonstrations ought to be interesting enough to help you know what is going on here. Okay, so let's get started. Let A, B, and C be constants, real numbers. Let the limit of f as x approaches a, and if you remember what a limit is, it's what the y values approach as the x values approach a. So we're going to let the limit of f as x approaches a and the limit of g exist as x approaches a, then any one of these 5 things will be true. The first one, and I think I've kind of left this, if you'll notice, I've kind of left this, the limit of a sum is, and I have over here, dot, 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 dot. I think that is probably the better way to remember this. I know, you're taking notes and you're going to madly copy all of this stuff down. But to be honest with you, I think it's probably better if you zero in on what we're about to talk about over here, okay? All right, so what is the limit of a sum? As you can see, I'm looking as x approaches a for the sum of these 2 functions, f of x plus g of x. What is the limit of a sum? So to show you that, and I think I have it right here. What I've got, and I'll try to make this clear if I can, what I've got here, and hopefully you can read all of this. Here is f of x equals x plus 1. F of x equals x plus 1 is this red line going up through there. It hits the y-axis at 1. The slope is 1, up 1 and over 1, up 1 and over 1, and so on. Okay, so that's the f function. And over here is the g function. G of x is equal to negative 2x. Negative 2x, try to come up with a different color for you. negative 2x is this blue line that's coming down like that, okay? And we are interested in what is the limit of the sum as x approaches 1 and x approaches 1 in both f and g. So what I want to do is get the sum of these two functions. I'm going to take x plus 1 plus negative 2x. X plus 1 plus negative 2x gives me negative x plus 1. If you graph negative x plus 1, negative x plus 1 hits at 1, has a slope of negative 1, which is down 1 and over 1, right? And as x approaches 1 in the red function, we know that the red goes to 2. As x approaches 1 in the blue function, it should go to negative 2, obviously. And as x approaches 1 here, you can see as it approaches 1 here from both sides, it goes to 0. Okay? Notice that 0 is the correct limit, and 0 is also 2 plus negative 2. So going back to what I just mentioned over here, I think the easiest way to remember this rule is that the limit of a sum is the sum of the limits. Okay? Yeah, I know this is correct mathematically. I'm not arguing with that. I think this is the easier way to remember it, and it'll be more valuable to you. Okay? All right. So let's go to the next one. And if I can keep everything straight here without going crazy, pardon me a second. Okay, the next one. The limit of a constant times a function. Limit of a constant times a function. That is when you take a function times some real number, okay? So the limit of a constant times a function, it looks like, just like up here with the limit of a sum is the sum of the limits. The limit of a constant times a function looks like the constant times the limit of the function. Okay, let's check that out with a demonstration just to show you that it works. Okay, and to show you that it works, I tried to pick functions that are a little off the beaten track, that they're not going to always be linear, that kind of thing. All right, so the first one I've got, and once again, I hope you can see this. My f function is the absolute value of x. And the absolute value of x is that traditional V shape that you should be used to. And that is done in red. Okay? Now, this is the limit of a constant times a function. So I must take this function and multiply times some constant. So I multiplied by a 2. Okay, so it's 2 times the absolute value of x, and I plotted some points, and I get this blue function for the constant times a function. Okay, so now what is the limit of the constant times a function as x approaches? We're approaching -1 in both of these. So as I come in on -1 here and -1 here, I can see that I'm at 1. When I come in on -1 here and -1 here, I can see I'm at 2, which is the correct answer, but it is also the limit of this one times the constant of 2 to give me the 2. Okay, so now we would be justified from this demonstration in saying the limit of a constant times a function is indeed the limit of a constant times a function is the constant times the limit. Okay, so the limit of a constant times a function is the constant times the limit. You can be sitting there right now. I'm sure you're sitting there saying, this is almost too easy. Yeah, sorry about that. It is almost too easy. Let's go to the third one. The third one is the limit of a product of two functions. Looks to be the limit of a product of two functions is the individual product of the individual limits, right? Did I say that correctly? The limit of a product of two functions would be the product of the two individual limits. Check out a demonstration of that and see if I have one of those. Yes, I do. Okay, so here's the limit, the two functions that I've chosen. Once again, if you can see this, this is x squared. You know that x squared, everybody has taken algebra 1, knows that x squared is that basic parabola type shape. Okay, that is my first one, and I'm examining what is the limit as x gets closer to 1. As x comes in to 1, the function also comes in on 1. The second function I've selected is x minus 1. This blue line right here is x minus 1. And as x approaches 1 in this one, as we approach 1, and as we approach 1, you can see that we are approaching 0. Okay? So what about the limit of the product? The limit of the product, I actually took the x squared times the x minus 1, and it gives you x cubed minus x squared. And I very carefully plotted points to show you this cubic. By the way, it's a positive cubic, so you know the end behavior is down on this side and up on this side. So here is that cubic. And you can see as I am approaching 1, this yellow function is approaching 0, which is correct. And it is also the product of the two individual limits. So going back to our list of rules, if I can handle this, limit of a product is the product of the limits. Okay, pretty cool. Works out really nicely. How about the limit of a quotient? You're on to me by now. You're saying the limit of a quotient is surely the quotient of the limits. Well, let's check it out and see if that works. And see if I have, here I have the limit of a quotient. So I've got to set up two functions. My first, and by the way, this was a little tricky because quotient can get to be a very ugly, nasty function. So I picked a nice, easy one to start with. F of x equals 4 is simply a horizontal line going through y equals 4. So, and I want to examine the limit as x gets closer to 2. And as x comes in onto here, and x comes in onto here, the function not only comes in toward 4, but it is 4. Okay. Now, what about my second function? Once again, trying to pick a simpler function to save me a little aggravation later. I picked g of x is x plus 1. Hits at 1, slope is up 1 and over 1. Blue line going this way. What is the quotient of these two functions? It is f of x over g of x, or it is 4 over x plus 1. If you very carefully plot points for this, okay, very carefully, and I think I neglected to mention, sorry about that. Let's go back here. As we approach 2 in this one, 2 and 2, you can see that I'm approaching 3 right up here. Okay, I'm approaching 3. Okay, back to the quotient of the two functions is 4 over x plus 1. And 4 over x plus 1, if you recall what we did in our last time together on unit 5, we talked about vertical asymptotes. And 4 over x plus 1, you're going to have a real problem if you try to put -1 in there. Okay, got a real problem. So very carefully sketching this, I get the yellow function which is asymptotic in both cases to x equals -1. And if you examine this function here, as we get closer and closer to 2, right? Look at it. Closer and closer to 2. You can simply put 2 in here because there's no problem of discontinuous function. There's nothing illegal going on. Putting 2 in here gives me 4/3, which is the correct answer. And lo and behold, 4/3 is precisely the quotient of the two limits. So now I can finish this rule, and I have the limit of a quotient is the quotient of the limits. Okay? I'm taking a bit more time on this than I would normally. Maybe it's because I'm feeling guilty because I'm not there, and I want to make sure everybody understands. Finally, the last one. How about the limit of a power? The limit of a power is the limit of a power here would be the power of the limit. Okay, I'm not certain if I have one of those to show you. Now, why do I not have one? Let's go back and check. There's my product. How did I mess that up? Okay, I do have one here. I have a particular power, okay? I have the cube root of x. If you can read that, that's the cube root of x. If you plot that cube root of x, if you remember pre-calculus, cube root is like a sideways cubic function, looks like that. Okay, we can take cube roots of negatives, so this does exist down here. Now, what we want to do is as we approach 8, 1, 2, 3, 4, 5, 6, 7, 8. As we approach 8 here, you can see that this is approaching 2. Okay, because the cube root of 8 is 2, obviously. Okay, where it gets fascinating then over here is I claim the limit of a root is the root of the limit. All right, the root of the limit. So now we're looking not at the limit of the cube root, but we are looking at, if I can just outline here, we're looking at simply the limit of x, which is a straight line. And I'm kind of off my graph here a little bit, but when you get way out here to 8, 8 goes to 8 in y equals x, right? So I'm up here at 8, 8, and the cube root of 8, eureka, it is 2. So it does work. The limit of a root or the limit of a power is the power or the root of the limit. We will put that back on our list if I'm not totally confused by now. The limit of a power is the power of the limit. Okay, so there are the rules. And as I said, I went to a little bit more detail on that than probably was necessary. All right, let's talk about some basic problems here that you're going to be seeing on your homework today. We can now use the limit rules to justify each step. So why don't we take a look at the limit as x approaches 2 of x squared minus 4 and talk about the steps to go through. I can see that this is a sum. This is the limit of a sum is the sum of the limits. So that would be the limit. I'm justifying each step as x approaches 2 of x squared plus the limit as x approaches 2 of -4. Yes, limit of a sum is the sum of the limits. That's a justification. I'm not writing that down. I assume that's easy. Next one, this is the limit of a power. We talked about that is the power of the limit. So this would be the limit as x goes to 2 of x squared. And this is the limit of a constant times a function, is it not? Isn't it a negative times a 4? So this would be plus negative the limit as x goes to 2 of 4. Okay. The function x, if you need to sketch it, the function x looks like that. as you head closer and closer to 2 here on the x-axis, you get closer and closer to 2 on the y-axis because it's y equals x. But then 2 squared is 4, okay? Plus over here, the limit of 4. Let's talk about the limit of 4. 4 is easy. It's just a horizontal line like this. As I approach 2 on this line, I'm approaching 4, or it is 4 everywhere, times this -1 is -4, and then I get 0, okay? And if you want to double check yourself, is that really the correct answer? Well, x squared minus 4, I'm running out of room up here, but isn't x squared minus 4 simply a parabola like this, right? Hits the x-axis at 2. So when I approach 2, aren't I approaching 0? Yeah, works, okay? A function is said to be continuous if it can be drawn without lifting your pencil. That is definitely not the mathematical definition, okay? But it makes a lot of sense. It is said to be continuous if it can be drawn without lifting your pencil. In other words, this is not continuous. You've got to lift your pencil, okay? Any breaks, holes, that kind of thing. So here's a very important theorem. A function is said to be continuous if and only if means that it reads both ways. If you have a continuous function with no holes, with no asymptotic lines, right? If you have a continuous function, you know that you don't have situations like this. And a continuous function, if you want to approach a certain value like c, you can simply put c into the function and get f of c, okay? Put c in. You don't have to worry about discontinuity here or asymptotic lines. So it goes back and forth. If you know that you can always stick the number in, you know it's nice and smooth and continuous. If it's nice and smooth and continuous, you know you can stick the number in. Okay, it goes both ways. Okay. All right, now here we come to the most important part. Some of these limit problems, they're going to get a little more interesting, shall we say. Okay, let's talk about this one up here. We have a problem, a real problem if x would happen to be -4, right? But we're not approaching -4 for crying out loud. We're approaching 3. And from what I just said, if we can stick the 3 in and get a value, okay, if we know that the limit is this, then we know it's continuous, and vice versa. If it's continuous, we know we can just stick it in. So if you go back to this, where is the discontinuity? Isn't the discontinuity at -4? Isn't that where there's a problem? Probably going to be asymptotic lines. At 3, there's no problem. There is nothing illegal about putting the 3 in. So let's just stick it in. This would become 9 minus 6 plus 5, which I think is 8. My brain is working. 3 plus 4 is 7. So there you have 1 1/7, or 8/7 is the limit as x gets closer and closer to 3. Everybody with me on that? Okay. How about this one? Now, we have a problem. Okay, we have a problem because if you put 3 in there, you're going to have division by 0. But all good algebra students should look at the top of that and say, hold on, isn't that x minus 3, x plus 3? Yeah. And now can't you kill the x minus 3s? So really, for the most part, this function is what's left, which is x plus 3. So let's talk about that. For the most part, it's x plus 3. What is x plus 3? Hits at 3. Slope is 1, which is up 1 and over 1. Okay, so we're tempted just to draw a line, right? But we got a problem here. For the most part, it's x plus 3. But we got a problem. 3 cannot be put back into the original function because you get 0 on the bottom. All right. For every other point, we're in good shape. But at 3, we got a problem. So at 3, and where does 3 go? Doesn't it go to 6? At 3, 6 up here, we cannot put the 3 in. So we have a hole in the graph. Okay. We have a hole in the graph. Now, as x approaches 3, I really don't care. As x approaches 3, here and here, the function is approaching the hole. The definition of a limit is what it approaches, not what it is. Remember? The definition of a limit is what y approaches, not what it is. So it still approaches 6. Okay? How about here? We have a problem. We can't stick 3 in. And this time we're not fortunate enough, we're not able to cancel anything out. Okay, so we better look at it from the right and the left. We're approaching 3. Okay, now because nothing cancels out, we have a problem at 3. It's not going to be a hole. A hole always is going to occur when you cancel something out. When you have something like this, it's almost always asymptotic lines. Okay, so I'm betting this is an asymptotic line. All right, and now watch what happens. As you come in from the right and you get closer and closer to 3, if you subtract 3 from numbers closer and closer to 3, like 3.1, 3.01, 3.001, aren't you left with very, very positive tiny fractions? Now, I know this is not very mathematically sophisticated, but it works beautifully. When you come in this way and you subtract 3 from all those numbers, you get positive tiny fractions. And when you divide by positive tiny fractions, when you divide 1 divided by, like a positive tiny fraction, like 1/10, don't you flip that and multiply? When you divide by a positive tiny fraction, you flip it and multiply, and you get horribly big positive numbers. So it is going to go up like this, big numbers. And when you come in from the left and you subtract 3, now you've got like 2.9, 2.99, 2.999. Now you get negative tiny fractions. 1 divided by negative tiny fractions, it's going to still flip it and multiply, but it explodes negatively. Okay? And you're down there like that. So what is the limit as x approaches 3? Positive infinity, negative infinity. It's not gone to the same thing. There is no limit for that particular problem. Okay? Asymptotic lines, when you can't cancel anything, you get a hole when you can cancel something. Okay? Over here, this would be an asymptotic line at -4. But because we weren't interested in -4, you didn't have to worry about going through that. Let's go down to these problems down here. And I'm running out of room, so I'll try to come down here. Okay, I made a correction here. It's 3 plus h quantity squared minus 9 all over h. As h goes to 0, we have a problem. We have a problem. Let's do some work on the top. Limit h goes to 0. Square this out. Square the first term. Multiply and double. Square the last term. Minus 9. The 9's kill each other, and I'm all over h. Amen? You bet. Now, doesn't something cancel out the h's? And I'm left with simply 6 plus h, the limit, as h goes to 0. Now, h can go to 0. We don't have division by 0 any longer. We don't have any problems, okay? Granted, because the h is canceled out, at 0, there's going to be a hole, okay? But no big deal. We can approach a hole. Answer is 6. All right. Oh, these root problems. These are a lot of fun. Okay, let's talk about this. Limit as x goes to 0. This is the square root of x squared plus 4 minus 2 all over x squared. Okay, it's a little fuzzy. I hope you can all see that. It is not apparent to me that anything is going to cancel out. So you might be thinking right away of asymptotic lines. But there's something we can do to this to make this a little bit more interesting. Do you remember how x minus 3 times x plus 3, remember algebra 1, x minus 3 times x plus 3, remember how you get x squared and negative 3x and positive 3x, they go away? Your outer and inners go away. These are called conjugates of each other, plus and minus, everything else is the same. So go back down to here. As long as I do the same thing to the top of a fraction as I do on the bottom, we should be okay. I'm going to multiply by the conjugate. Same thing on the top and bottom, yes? Okay? Now do the same thing you did up here. So here we go, let's FOIL it. A root times a root is just the thing. The root goes away. On the outers, I get a positive 2 times this. On the inners, I get a negative 2 times this. They go away. And then I'm left with negative 2 times 2 is minus 4. Will you look at that? On the bottom, I have x squared times the root of x squared plus 4 plus 2. And don't even bother multiplying it out. These babies go away. The x squareds cancel. I'm left with the limit as x goes to 0, 1 over root x squared plus 4 plus 2. And look at this now. 0, putting it in for x, does not cause 0 on the bottom. There's nothing illegal going on here. You can put 0 in, you get root 4, which is 2 plus 2. And the answer, the limit is 1/4. Okay, that works on even this one up here. For this one up here, I would multiply top and bottom by the conjugate, which is going to be root x plus 25 minus 5 and plus root x plus 25 plus 5. On the top, we have the limit as x goes to 0. Once again, the issue is because x can't go to 0. You get illegal division by 0. The roots go away. I get x plus 25. Outers and inners, positive 5 times the root, negative 5 times the root, negative 25. Look at that, they go away. And then I can cancel the x's, and I'm simply left with that on the bottom, x plus 25 plus 5. Now you can put 0 in with no problem. The root of 25 is 5 plus 5 would be 1/10. Okay? All right, I am really running out of room here. See if I can use some more of my paper. All right, do right and left hand limit arguments. F of x equals root x. When x is bigger than 4, is root x. When x is bigger than 4, and it's 2 when x is less than 4. So here we are at 4. When you're bigger than 4, strictly bigger, we can't use 4. I'm going to do it anyway. Square root of 4 is 2. So I'm going to go up 2 and put a hole because it's not equal to 4. Okay, so when x is bigger than 4, square root of x. So the square root of 5 is a little bigger, square root of 6 a little bigger, square root of 9 is 3, and so on. This looks like that. It's like a sideways parabola starting there. Okay, now when x is less than 4, can't use 4 again, but it does go to 2. Open circle. It goes to 2, so it's got to come down like that. Okay. The limit of f as x approaches 2 from the right, the limit of f as x approaches 2 from the left. Left and right hand limit argument. We're going to evaluate both sides. As you come in from the right, this thing is approaching 2. Now, wait a second. I want the limit And I don't think I really specified where I wanted the limit, but I wanted it 4. My apologies. This should say, what is the limit as x goes to 4, not 2. Pardon me. Senior moment. Okay. So as x goes to 4 from the right, this comes in on 2. As x goes to 4 from the left, it is 2 the whole way. They're both approaching a whole, which is not a problem. So the answer, the limit of f as x approaches 4 from both directions is 2. Okay. Let's come down here. What's the limit of the absolute value of x? Real easy. You know that absolute value is that V shape. Okay, so the limit of absolute x as we approach 0 from the left, and the limit of absolute x as we approach 0 from the right. Okay. All right, as we come in from the left, this curve is approaching 0. As we come in from the right, this curve is approaching 0. Put it all together. The limit as x approaches 0 from both sides is in fact 0. Okay, one more. This one is a little interesting. So let me get another piece of paper out here. Okay, here we go. The last one. What about the limit as x approaches 0, x over absolute x? All right, let's do a little bit of a sketch of this. Obviously, we can't put 0 in here because it's going to be undefined, division by 0. And it's a little tricky canceling. Okay, so let's do a sketch. As you come in, we're going to do the limit as x approaches 0 from the right, the limit as x approaches 0 from the left of my function. Okay, as I come in from the right, I'm coming in this direction. What does this thing look like? I have like 5 over the absolute value of 5 is 5. 5 over 5. I have 4 over 4, 3 over 3, 2 over 2, 1 over 1. It can't be 0, but I know they're all the same numbers. They're going to divide, and it's the line that is y equals 1. It comes in here, and there's an open circle because we can't put 0 in. And when you do from the left, it's exactly the kind of the same, except one of these is going to be negative. Like, for instance, -5 is on the top, but the absolute value of -5 is 5 on the bottom. Okay? So this becomes -5 over 5, -4 over 4, -3 over 3, and so on and so on and so on and so on. Yeah, you with me? So this is -1, comes in like this, and you can't use 0 again. So there's a hole there. So we know here it's approaching +1. We know here it's approaching -1. Put that all together. Limit as x approaches 0 from both sides of x over absolute x is undefined. When you do a right and left-hand limit, I want to see all 3 parts of this. This from the left, from the right, boom, from both sides. Okay? All right, homework is in your booklets. Answers to the problems will be on Blackboard. And we'll see you Monday.